Welcome to our session on superconductivity, number representation, and Majorana physics. Today, we are going to focus on systems that show superconducting order. This is an order that arises due to electronic interactions in quantum many-body systems, and in particular that give rise to spontaneous breaking of gauge symmetry. The learning outcomes for today are going to be first to recognize what is the nature of a superconducting state and what are the types of interactions that give rise to a superconducting state, to understand excitations in superconductors using the Nambu formalism, that it's a formalism that allows you to combine electron and hole excitations in a Hamiltonian to find what are the eigenstates of a superconducting Hamiltonian. And finally, we will use this formalism to show that a very specific type of superconductor, called a topological superconductor, can show Majorana excitations that are very interesting for topological quantum computing. As a reminder from previous sessions, let us recall that if we have materials that show electronic interactions, quantum many-body interactions, then we can have a phenomena that is called spontaneous symmetry breaking. What this actually means is that you start with a Hamiltonian that has all these symmetries that you wish, but then electronic interactions give rise to a ground state that breaks some of these symmetries. And depending on the symmetry that you break, you obtain a completely different electronic order. If you break the transversal symmetry, then you get a ferromagnet or antiferromagnet that has associated quasi-particle excitations that are called magnones. If you break translational symmetry of your lattice, you effectively get a charge density wave that gives rise to more charge accumulated in some sites and less charge accumulated in other sites. And the material that we will focus on today, which is the case of superconductors, which in particular break gauge symmetry, which is this symmetry that is associated with the phase of your wave function. Usually, we think that the phase of the quantum many-body wave function is not physically observable. In superconductors, this phase is the object that gets broken. Superconductivity is one of the correlated states of matter. And the fundamental idea is that if you have a Hamiltonian that has kinetic terms, like hopping term, that it's a bilinear term, like the one that you see here on the top, then apart from this single particle term, you can have many body interactions. There are terms that are biquadratic in the fermionic operators. The way in which we can deal with this Hamiltonian is, on one side, we can do our mean field approximation that consists simply on taking this term that has 4 fermionic operators and take averages between them so that we end up with a term that it's only quadratic. And if we do this, we can describe many types of systems like magnets and superconductors, of course, and charge density waves. When we are able to do this to compute and to capture a certain phenomenology, then we say that we have weakly correlated matter. So we have a ground state that can approximately be represented as a single particle state. A single particle state, of course, with a very specific single particle Hamiltonian. This is the case of superconductors, and this is the case that we are going to focus on today. Of course, there's another case where mean field actually doesn't work, and this is the case of strongly correlated matter. In these cases, there's no good mean field Hamiltonian that is capable of capturing the phenomenology that you are interested in, and in practice, you would need to solve the problem exactly analytically if you are lucky, and in general, using a numerical solver. And this is, of course, one of the cases that we saw in some of the previous recordings, for example, the case of the fractional quantum Hall effect. So every time that we think about a symmetry broken state, we usually think in terms of a single particle mean field Hamiltonian that has an additional term created by interactions, and this additional term is the one that breaks the symmetry. In the case of magnets, we would have a additional term that breaks transversal symmetry. In the case of charge density waves, we would have an additional term in the Hamiltonian that breaks the original translational symmetry of the lattice. And in the case of superconductors, we have a term that breaks the gauge symmetry of the Hamiltonian. That is this term that you see over here with two create annihilation operators, and of course, the Hermitian conjugate that has two creation operators. One of the interesting points of correlated states, and in particular, both mean field states and strongly correlated states, is that they can give rise to completely different properties. So superconductors are a type of correlated state that can be described using a mean field description, and these types of states, they actually are usually created by some existence of an attractive interaction in the Hamiltonian. So every time that you have superconductivity, you have some quasi-particle or some interaction in your Hamiltonian that helps electrons get closer to each other. And of course, superconductors have the property that they are destroyed by magnetic field. So a magnetic field is often incompatible with a superconducting state. Superconductors can have a very specific type of fractional excitation that it is called a Majorana bound state, and that it is the state that we are going to address today. Of course, in some of the previous recordings, we already saw a different type of fractional excitation, which is the fractional excitation that appears in the fractional quantum Hall state. In contrast with superconductors, the fractional quantum Hall state does not have a mean field description, and instead of being created by attractive interactions, it is created by strong repulsive electrostatic interactions, and instead of requiring no magnetic field, it actually requires, in most of the instances, strong magnetic fields, although of course you can also have it at zero magnetic field, and yet it shows fractional excitations. Fractional excitations can appear, therefore, in two completely different regimes. They can appear in cases where you don't have a mean field description and you require repulsive interactions from magnetic fields. They can also appear in cases where you do have a mean field description and you have instead attractive interactions and you don't want to have magnetic field. This is one of the examples where we can actually have widely different phenomena in completely different regimes, and yet that they share some of the properties in terms of emergence, and in particular, in this case, the property of being a fractional excitation. Of course, it is important to keep in mind that Majorana excitations are completely different from the fractional excitations in the fractional quantum Hall state, but they are in a way a fraction of an electron, although in, let's say, different ways. There's one extremely important point about superconductivity, and this idea is the idea that superconductivity is one of the macroscopic quantum states that we can find in nature quite easily. And by macroscopic quantum state, what I actually mean is that you have a system that it's made of trillions and trillions and atoms, and yet when you make a measurement, you see directly one of the microscopic constants that the material depends on, which are the Planck's constant and the charge of the electron. And this type of measurement is actually related with the measurement of the quantum of flux in a superconductor. And the reason why this measurement is protected is very much related with the breaking of gauge symmetry in the wave function. Superconductors have a wave function that breaks gauge symmetry, meaning that it has effectively a single phase. Now, if you think that you go on a closed loop around a hole in a superconductor, and in particular around a hole in the superconductor where there's a finite magnetic field, then the fact that your wave function has to be uniquely defined automatically enforces that the flux that you have inside that circle must be a quantum of flux. And this mathematical property, the mathematical property that the wave function has to be single valued, gives automatically quantization of flux and actually impacts the measurement of critical currents in Josephson junctions. And this is one of the ways to obtain the ratio between the Planck constant and the charge of the electron. The other way of accessing these two microscopic constants was with another different macroscopic quantum state, which is the quantum Hall effect or the Chern insulating state. In this state, we actually had a single particle description that was topological and in particular gave rise to the quantization of conductance from the fact that the conductance was proportional to the Chern number of the electronic structure. And what's important is that this quantum of conductance depends on the charge of the electron and the Planck's constant. This measurement is again a macroscopic measurement. You take a material that it's made of billions and billions of atoms and you obtain the ratio of these constants. And now by combining these two measurements of the quantum of flux and the quantum Hall conductivity, you can effectively extract the values of both the Planck constant and the charge of the electron. And in particular, these are one of the most accurate ways to extract these two fundamental constants. Measurements of microscopic quantities, like the charge of electron and Planck's constant, essentially leverage this idea of emergence in quantum materials. Okay, now let us move on to the theoretical description of superconductivity. And the idea for this is that first we need to understand what is a superconducting state. So what are the physical properties that superconducting states are? And then once we know those properties, we can come up with the Hamiltonian that is capable of describing such a phenomenology. Superconductors are materials that show a sudden drop in resistance at a certain temperature. And of course, this is the way in which they were discovered. So the idea is that if you have a metal has a high resistivity at high temperatures, and as you lower the temperature, the resistivity of the metal goes down. This is simply because you have less phonons in your material and electrons scatter less with the phonons. And in a superconductor, what you actually have is that, of course, the resistance also goes down with temperature, but at a certain critical temperature, it completely drops and then it stays zero, even at low temperatures. This drop of the resistivity is what is associated to the superconducting transition. And the temperature at which this drop happens is what is called the critical temperature of the superconductor, and it's the temperature at which we have gauge symmetry breaking. One of the important properties of superconductors is that they have something called Meissner effect. And the idea is that if you have a metal that is in a magnetic field, in principle, a metal is compatible with a magnetic field, so nothing happens if you are above the critical temperature. But then once you go below the critical temperature of the superconductor completely expels the magnetic field, and the only magnetic field remaining inside the superconductor must be in quantized vortices, at least in type 2 superconductors. And this is another signature of the superconducting state, and this is directly a consequence of gauge symmetry breaking. Let us now look at the typical Hamiltonian for a superconductor, and it is fair to say the typical Hamiltonian of strongly correlated matter. So we have a free Hamiltonian term that contains mainly kinetic energy, and then we have a term that contains the interactions, VI, JKL, C dagger I, CJ, C dagger K, CL. And in this term, we can have all sorts of interactions in the material, anything that can couple two electrons together. Of course, this can be the electrostatic interactions that we have already classically, but we can also include here interactions that are mediated by some quasi-particles. So if you think that you have a material that has atoms and in particular have nuclei, then the nuclei can sort of vibrate and they can effectively mediate interactions between electrons. These are called phonons, and this interaction mediated by the phonons is what it's called electron-phonon coupling. But we can also have any other sorts of quasi-particles. So if we have a magnet that can have fluctuations of the magnetic moment, then these fluctuations of the magnetic moment can also couple to electrons. And this can also be included in this term if you have a system that has charges, like most of the metals, we can also have plasmons, which are collective fluctuations of the charge, and this can also mediate interactions between electrons. If we have exotic magnetic states such as fermions, then we can also have fluctuations of these fermions, and this can give rise to other attractive interactions and so forth. In general, if you have any quasi-particle in your material, you can think that this quasi-particle is going to couple two electrons in a very specific way, and it may be able to mediate interactions between electrons. What is important to know for superconductivity is that regardless of the nature of the quasi-particle or interaction that gives rise to effective interaction between electrons, superconductivity requires some channel that is attractive. And this might mean that for some collective emergent reason, electronic repulsions becomes suddenly attractive at certain wavelengths. This might mean that phonons can mediate attractive interactions. This might mean that any quasi-particles mediate attractive interactions, and so forth. So overall, we divide superconductors into two different types. And these are related with what is the origin of the attractive interaction. The most well understood interaction is the case of electron-phonon interaction. So interactions mediated by fluctuations in the lattice. These types of superconductors are called conventional superconductors, and they have a symmetry breaking that we understand pretty well, and it is possible to predict some of the critical temperatures of simple conventional superconductors. So we know that our theory, even though it is a mean field theory, it is actually relatively accurate for capturing conventional superconductors. In this conventional superconductor, you have aluminum, lead, most of the superconducting metals. Then the most exotic superconductors are actually called unconventional superconductors, and they are essentially mediated by quasi-particles that are not phonons. So they can be mediated by fluctuations of the magnetic moment in an antiferromagnetic system, such as antiferromagnetic magnons. They can be mediated by fluctuations of the magnetic moment in a ferromagnetic system, such as ferromagnetic magnons, or plasmons in a charge density wave state, or valence fluctuations in materials that have valence order, or charge fluctuations in materials that also have charge density wave, and many others. When you have some attractive interaction that's mediated by some exotic quasi-particle, very often you may end up with an unconventional superconductor. Unconventional superconductors are a major open challenge. We do not have a good theory to predict them. We are not capable of predicting what are the critical temperatures of systems that are unconventional superconductors, even though we tried for many decades. And it is fair to say that it is even hard to identify what is the mechanism behind unconventional superconductivity, and in particular to identify what is the specific quasi-particle that is mediating the attractive channel. So now it is a good point to start with our simplest interacting Hamiltonian. And the simplest interacting Hamiltonian that we can consider is for example, one-dimensional chain that has hopping between the sides. So you can think that Tij is hopping between first neighbors, and then we have some local interaction. This is the simplest form of many-body interaction. Now, the idea is that this Hamiltonian, even though it seems relatively simple, it can already have two different states just depending on what is the value of the many-body interaction that you consider. If you have an effective attractive interaction, then when you do mean field, you will end up with a superconducting state. In contrast, if you have an effective repulsive interaction, then when you do mean field, you will end up with a magnetic state. Today, we are going to focus on superconductivity, but we will see in the next recording that you can also get magnetism from this very same Hamiltonian. And the way to get superconductivity is relatively simple. So you take your Hamiltonian, and in particular, you take your biquadratic term in the Hamiltonian that has two creation operators and two annihilation operators, and then you ask yourself, well, I do not like to have biquadratic Hamiltonians. I want to have bilinear Hamiltonians. So the way I go from biquadratic to bilinear is just by taking expectation values. This is what we call the mean field approximation. And when you do that, you should technically take all the possible combinations of two operators, but the combination that matters for a superconducting state is the one that has either two creation operators or two annihilation operators. When you do that, you end up with a mean field Hamiltonian that has a certain parameter delta times 2 annihilation and the Hermitian conjugate, of course. And this parameter delta is the expectation value of C dagger, and this is what we call the superconducting order. A superconductor has a non-zero expectation value of this delta, and a system that is not superconducting has a zero expectation value of this delta. And of course, this delta is exactly the term that breaks gauge symmetry in our superconductor. So now what we have is a Hamiltonian that has our conventional single particle term, so C dagger C. And then we have this additional extra term that appeared due to the many-body interaction that is CC. So it's a bilinear term, but it is not a term that has creation and annihilation. It has two annihilation operators, and of course the Hermitian conjugate has two creation operators. So now let us look at this term a little bit more in detail to understand which symmetries does it break. If you have a Hamiltonian that has a term that has two annihilation operators, what you automatically know is that your ground state cannot have a constant number of electrons. And the reason for this is relatively simple. So you can take your eigenvalue equation for the Hamiltonian with Gs, the ground state of the Hamiltonian. And now if you want this state to be an eigenstate of the Hamiltonian, then you need to have a system that when you destroy two electrons or you create two electrons, you end up with the same state. Of course, this is only true if you have a combination of 2 electrons and 4 and 6 and 8, so that when you create 2 and destroy 2, you just shift around the term in the right. Of course, you can have either an even number of electrons, so 2, 4, 6, 8, and so forth, or you could have an odd number of electrons, 1, 3, 5, 7, and so forth. This is a consequence of gauge symmetry breaking. And it is a consequence of gauge symmetry breaking because gauge symmetry is the symmetry that guarantees that particle number is a good quantum number. Once you break this symmetry, then your eigenstates of the Hamiltonian are no longer eigenstates of the number of electrons. And at the mean field level, a superconductor has a fluctuating number of electrons. So now it is interesting to relate this type of symmetry breaking to an actual transformation in the Hamiltonian. And for this, it is interesting to just explicitly write down how the gauge transformation acts on the creation or the annihilation operators. So usually the way we think about gauge symmetry in first quantization is by saying that the phase of a wave function is not does not have physical significance, so it is not something that we can measure. So if we try to translate this to a second quantization formalism, then this gauge symmetry essentially becomes this notion that you can take your annihilation operator and add one phase, or you can take your creation operator and add the opposite phase. This is a gauge transformation. What you can quickly see is that most of the mean field terms in the Hamiltonian do not break that symmetry, specifically because you have C and C dagger, and when you have C and C dagger, these two phases cancel out. So in particular, hopping does not break gauge symmetry, any sort of magnetism does not break gauge symmetry, any sort of spin-orbit coupling also does not break gauge symmetry, and of course, many-body interactions also do not break gauge symmetry. But the superconducting state does break gauge symmetry. And this is something that you can very easily see just by making this transformation explicitly in your order parameter for a superconducting state, that it's C dagger, C dagger. So the idea is that when you just replace C dagger by the transform, you pick the phase twice. So the superconductor breaks gauge symmetry. And this is, again, just a consequence of the fact that you have two creation or two annihilation operators. We now know what are the basics of a superconducting state. So now it is interesting to move on to the formalism that we can use to understand the excitations of a superconducting Hamiltonian, and of course of a mean field superconducting Hamiltonian. So in general, a superconducting Hamiltonian takes this form. So we have a term that is our conventional single particle term that has creation and annihilation operators, and then we have our other term that has two creation or two annihilation operators. What we have to do now is to diagonalize this Hamiltonian, and of course we cannot diagonalize this Hamiltonian in the conventional way of just creating a, let's say, a vector that has as many components as orbital we have in the unit cell, because now there's this additional term that has two creation operators and two annihilation operators. This can be actually solved fairly easily just by defining an enlarged, let's say, vector, if you will. So the idea is that you define a spinor operator that takes this following form. So the upper part is your conventional annihilation operators, and then you make a copy so that you have creation operators. And now the basic idea is that the previous Hamiltonian that you have can be written just as a product of psi dagger H psi, where now this H is a 4x4 matrix. So if you have an electronic structure that has, for example, a single orbital per unit cell, and you write this down in reciprocal space, then a single orbital per unit cell gives rise to, let's say, one orbital for spin up, one orbital for spin down. And when you add your Nimbus spinor, you have an additional copy of up and down, but for the whole sector. So one orbital per unit cell with two spin components gives rise to a 4x4 Hamiltonian. So to diagonalize a superconductor, to find the eigenstates of a superconductor, you simply have to diagonalize this 4x4 matrix. And the idea is that the elements of this matrix can be very easily read just from the Hamiltonian directly. So the dispersion of your electrons, which is epsilon k, appears in the diagonal, and in particular, it appears in this diagonal upper left part, and it appears again in the diagonal down part, because of course you have the same term, but with the opposite ordering of creation and annihilation, and you do intercommutation relations of the fermionic operator, you can reverse it so you get it twice. And then in the off diagonal, then you get the pairing term. So if you now consider this Hamiltonian, multiply by psi and multiply by psi dagger, you will see that you are going to recover this original Hamiltonian that we have over there. So in practice, if you want to diagonalize a superconductor, if you want to find the eigenenergies and eigenstates of a superconductor, you simply have to write down this 4x4 matrix of course, if you just have a single orbital and diagonalize it. This is what it's called the Bogoliubov-de-Gennes Hamiltonian. And to understand electronic excitations in superconductors, this is effectively the most fundamental object that we can use. So now let us look at the electronic structure of some superconductors using this Bogoliubov-de-Gennes Hamiltonian and these Nimbus spinors. And let us start with the simplest example, which is a one orbital model in the square lattice, which gives rise to this dispersion that is cosine of kx plus cosine of ky that you see plotted over here. Let us imagine that we put the chemical potential so that the bands are crossed at this point that you see over there. And what we do now is we switch on the Nimbus spinor. So we do not have superconductivity yet. You can imagine that you take your Bogoliubov-de-Gennes Hamiltonian and put delta equal to 0, but you make this replica of the, let's say, electron sector into the whole sector. Since the whole sector has an opposite dispersion at the electron sector, you are now going to get two copies of your electronic structure. You're going to get your physical copy, that is the band structure that is shown here in red, but then you have this spurious copy, that it's this band structure in blue that comes from the value of the Jens Hamiltonian. Again, it comes from the fact that you have a lower right part of your matrix with exactly the opposite dispersion as the upper part. And now, once you switch on superconductivity, which is the term that appeared in the off diagonal, what you essentially get is that a gap opens up. In a superconductor, you need to pay a finite amount of energy to put a single electron. You don't have to pay any energy if you insert 2 electrons, but if you want to insert a single one, you need to pay a finite amount of energy. And this gap here that you see is the energy that you need to pay to insert a single electron. And of course, this gap is the superconducting gap, the object that broke gauge symmetry in our state. What is important of superconductors is that this gap opens up regardless of what is the specific electronic dispersion that you have, regardless of whether you have first or second neighbor hopping, regardless of where your chemical potential is. This is just because the Bernoulli of the Jens Hamiltonian enforces this symmetry that creates this additional copy of your band structure, and at the crossings between the physical copy and the spurious copy, you always get a gap opening due to superconductivity, at least due to conventional superconductivity. So if you think, for example, about a triangular lattice that has this spectral function that you see here in the slides, and as you change the chemical potential, you are effectively just changing the location of zero with respect to your dispersion. Now you can see that if you add superconductivity and you project onto the electron sector so that you only see the physical states, you see that a gap opens up all the time, regardless of what is your chemical potential, regardless of where your bands are crossing. And again, this is just a consequence of the Bernoulli of the Jens Hamiltonian. This is a consequence of the electron hole symmetry and the pairing of the Hamiltonian. You can do that also with the square lattice. So you can take your square dispersion, change the chemical potential, and see that once you introduce pairing in the Bernoulli of the Hamiltonian, then a gap opens up regardless, again, on what is your chemical potential. So superconductivity, at least conventional superconductivity, always opens up a gap in the electronic structure. So the only thing that you need to get a superconductor is a attractive interaction, so or some channel that gives rise to this attractive interaction. And then if you have some states close to the chemical potential, then you will open up a superconducting gap. There's, of course, a very special type of superconductivity, which is so-called unconventional superconductivity, and as a specific example, nodal superconductivity. So this superconducting state is a superconducting state that opens up a gap only on specific places of the reciprocal space. So here you can see one case of an unconventional nodal superconducting state that opens up gaps in this region of reciprocal space, but that keeps this region of this reciprocal space effectively as a metal. So nodal superconductors are, in a way, systems that behave like gap superconductors in some regions of reciprocal space, but in other regions of reciprocal space, they sort of behave like metals. And in particular, high temperature cuprate superconductors, they belong to this family, the family of gapless superconductors. So if you think about the specific electronic dispersion, like this one shown over here, in terms of superconductivity, there are, let's say, 3 possible scenarios. You have the scenario in which superconductivity does not exist, and you have a metal, which is the one that you see on the left. You have the scenario where you have conventional S-wave superconductivity, and in this instance, you open up a full gap in reciprocal space. And then you have the case where you have unconventional superconductivity, which is the case where you open up gaps in some parts of the reciprocal space, but other parts of reciprocal space, they remain gapless. And now, this is something that, of course, it applies also to not only the square lattice, but also the triangular lattice. So in the triangular lattice, you can also have these 3 different scenarios. You can have a case where you don't have no superconductivity whatsoever. You can have a case where you have gaps everywhere in the Brillouin zone, and you can have a situation where there's a gap in one part of reciprocal space, and then the other part of reciprocal space remains effectively gapless. So now we've seen our first instance of unconventional superconductivity, which was this superconducting state that gapped some parts of reciprocal space, but not all of them. Let us look a little bit more in detail at unconventional superconductivity. So the idea for unconventional superconductivity is that you can take a more generalized Hamiltonian to observe superconducting states. So instead of considering that you only have pairing between electrons on the same side between the up and down channel, you can now consider that you can have electrons, a gap function that is not only on side, but that it also changes in reciprocal space, and that it can have different types of indexes. So you may have up down, but you may also have up up. So in general, this type of Hamiltonian is going to appear as the mean field Hamiltonian of some complicated interacting electron model. In the following, we are not going to worry about the specific electronic model. We are not going to worry about the specific many-body interaction, but we are just going to take as a starting point our mean field Hamiltonian. And in particular, we are going to take as a starting point the mean field superconducting order that now it's going to have several components. It's going to have one component that it's up down, that it's very similar to the one that we considered before, but it also has one component that it's up up and another component that it's down down. And these components can be momentum dependent. Unconventional superconductors essentially show different structures for these different components. And so you can think that unconventional superconductors are systems that show a non-trivial dependence on momentum space in their superconducting order parameter, or if you Fourier transform back, that they have some unconventional dependence in real space for the superconducting order parameter. Both pictures are effectively the same, so you can just do a Fourier transform and go from one to the other. In practice, it is usually convenient to work in reciprocal space for the superconducting order parameter, but you can also understand it in real space. And the trick is that you can classify different types of superconducting order just by looking at the symmetry of the superconducting order parameter. So the symmetry of the superconducting order allows you to tell which kind of superconductivity you have, and even how the superconductivity is going to respond to perturbations into magnetic fields. All this just from the symmetry of the order parameter. So if we think about, let's say, the different symmetry characterization that we can have for our order parameter, there's one relatively simple symmetry characterization, which is essentially asking yourself what happens if you switch the order of your spin indexes in the superconducting order. If you look at the definition of the superconducting order parameter, you will see that due to the anti-commutation relations of fermionic operators, then you are going to pick a minus sign in K and a minus sign in front, regardless of whether you have up, up, and down, and so forth. This is just a consequence of fermionic statistics. But you have some degree of freedom when choosing what happens when you switch the indexes and you switch the value of K, in particular when you switch the sign of K. And there are two scenarios. There's the scenario where you actually get an even superconducting state, meaning that when you switch K by minus K, effectively your superconducting order remains the same. This is what happens, for example, for S-wave superconductors, which is the first superconducting state that we saw today, the one that appeared due to local attractive interactions. And then there's the alternative case, which is the case in which you actually pick a minus sign when you switch the sign of K. This is the case of odd pairing or spin triplet superconductors. So if you look at very specific orders, what you actually have is that conventional superconductors belong to this type of spin singlet even order, meaning that it doesn't change sign in reciprocal space, and in particular something that is constant doesn't change sign. And then there's the other case of unconventional superconductors, which is spin triplet superconducting order, in which if you change the value of k, or if you change the sign of k, you essentially pick a minus sign on your superconducting order. And this symmetry property is essentially what allows you to characterize your superconductor. And this symmetry property has massive consequences. For example, this type of superconductor that you see on the left, spin singlet superconductor, is not sensitive to local non-magnetic disorder. Whereas this superconductor that you have on the right, it is very sensitive to non-magnetic disorder. So if you have a material and you see that it's superconducting, but that it is very sensitive to having non-magnetic impurities, then you know that probably is going to be some odd superconducting state and perhaps a spin triplet. Whereas if you see that the material is very resilient to impurities, then you are going to have a spin singlet state. And this notion can already tell you why in nature it is so much easier to find spin singlet superconductors than spin triplet, or S-wave superconductors than spin triplet. So if you have a material that has many impurities and, let's say, imperfections, then unconventional superconducting states are going to be quickly quenched because they are, let's say, very damaged by non-magnetic scattering. Whereas spin singlet superconductors, they are going to be resilient. So you can actually have relatively disordered superconductors that show spin singlet S-wave superconductivity. Okay, so now let us look at some, let's say, more generalized Hamiltonian. So let's imagine now that you have a material that has kinetic energy, has attractive interactions, but that also is magnetic. So this is like a magnetic metal, but that it happens to have attractive interactions. Then when you look at this Hamiltonian at the mean field level, you're going to get something that is superconducting, but that it's magnetic at the same time. And this is what spin triplet superconductors are. Spin triplet superconductors, they can actually be systems that break simultaneously time reversal symmetry and gauge symmetry. And this is something that it is relatively easy to do with a toy model. So you start with your Hamiltonian for a ferromagnetic system where you introduce your exchange field by a term like this. And then afterwards, you introduce your attractive interactions. And you can now solve this at the mean field level. And when you solve this at the mean field level, what you actually observe is that a gap opens up between the electron and the hole sector, which is this gap that you see over here. So now you have a superconducting state, but at the same time, you have a system that is magnetic because of this term. So this type of self-consistency effectively gives rise to a spin triplet superconductor. So usually spin singlet states are the ones that dominate. S-wave superconductivity is the leading instability in a superconducting state. And this stems from the fact that S-wave superconductivity gaps your whole Fermi surface, so you actually gain the maximal amount of condensation energy. If you want to have a spin triplet superconductor, you often need a mechanism that quenches the original mechanism given to S-wave superconductivity. And in this example over here, the mechanism that quenches S-wave superconductivity is this exchange field. So once you quench S-wave superconductivity, then other superconducting channels like the P-wave channel, for example, spin triplet channel, can become the leading channel and give rise to a superconducting state. And that is exactly what is happening over here. Now, something massively interesting of this spin triplet superconducting state is that if you look at the electronic structure of the superconductor in a finite geometry, in a ribbon, what you actually see is that in the bulk, there's a gap, which is what you see over here. But then at the edges of the system, you actually have gapless excitations. And let me emphasize again that this is a superconducting state, and that when you measure it in the bulk, you see a gap. When you measure it at the edge, you see gapless excitations. Of course, the nature of these gapless excitations is essentially topology. So these unconventional superconductors effectively have topological states, and these topological states are associated to a finite Chern number. Okay, let us now analyze another type of, let's say, unconventional superconductivity. So instead of looking at singlet and triplet states, we could focus on just a singlet order. So an order that it's even in momentum space, delta up down. But even though it is even in momentum space, it can have actually two different structures. So we can have a superconducting order that it's always non-zero in reciprocal space. And this is the case again of S-wave superconductors that corresponds to most of the elementary superconductors that we have in nature, such as lead, aluminum, and let's say metals that become superconducting at low temperatures. But then there's an unconventional superconducting state that it's a singlet, which is the so-called gapless superconducting state, and in particular a state where instead of having an S-wave pattern in reciprocal space, we have a D-wave pattern. So a pattern with L equal to 2 in reciprocal space. And this is the case of cuprate high temperature superconductors. So many of the superconductors that show critical temperatures on the hundreds of Kelvin, they are spin singlet superconductors, but not S-wave superconductors. They are D-wave superconductors. They are gapless, and the gap closes in some points of the Brillouin zone. Overall, one of the interesting ideas in the superconducting gap is that you can classify this gap according to how it changes in reciprocal space. And the idea for this is exactly the same as in atomic physics. You can think about a spherical harmonic basis for whichever quantity you want. In our case, is the superconducting gap. In atomic physics, is the wave function, and you can perform expansion in this harmonic basis. If your leading term is S-wave, then you say that it's a conventional S-wave superconductor, and these types of superconductors are very often driven by phonons. And if you have a system that is phonon driven, it is very, very likely that it will end up to be an S-wave superconductor. Then you can have L equal to 1 profile in reciprocal space, and this gives rise to P-wave superconductivity, which is one of the cases of spin triplet superconductivity. This is in general an unconventional superconducting state and is the one that is often, but not always, driven by ferromagnetic spin fluctuations. And in particular, the topological superconductor that we saw before is a specific case of a P-wave superconductor. And then we can have even higher angular momenta for our superconducting order. We can have D-wave superconductors that essentially show the same profile in real space as our conventional d orbitals in atomic physics. And these are also another type of unconventional superconductors. And these are sometimes, but yet not always, driven by antiferromagnetic magnons. And this is the case, for example, of cuprate high temperature superconductors. It is perhaps easier to look at these orders in reciprocal space. So for example, if you look at the S-wave superconducting order in reciprocal space, you essentially see something that is constant, that it's flat, so there's no momentum dependence whatsoever for an S-wave superconductor. If you look at a dx squared minus y squared d-wave order, and this type of nomenclature comes exactly from atomic physics, you essentially see something that has finite superconductivity in some regions of reciprocal space, but suddenly it becomes exactly zero at some nodes. And there's actually an alternation in the sign of the superconducting order. So here is plus, here minus, plus, minus. And then you can also have other orders that are actually also nodal, but they are S-waves. And this is, of course, the case of the extended S-wave superconductor, which is a system that has, let's say, positive superconducting order here around the gamma point, but then it has a node at a certain point, and then the superconducting order becomes negative. So if you do an expansion in spherical harmonics, you see that the L equal to 0 has a non-zero weight, but you still have a nodal order, at least in the radial direction of the momentum. You can do this very same classification also for other lattice symmetries. So if you think about the triangular lattice instead of the square lattice that we showed in the slide before, then you can see that S-wave superconductivity is something that is uniform in reciprocal space. You can have something that it's nodal F-wave superconductivity, so L equal to 2, and that has signs plus, minus, plus, minus, plus, minus. And then you can also have other superconducting states like extended S-wave superconducting order, that it's plus here, then it becomes 0, and then it becomes minus over there. Something very interesting is that you can have different superconducting orders that have very, very similar spectral properties. So here you can see, for example, the case of an electronic structure that has an S-wave superconducting order, so non-zero everywhere in reciprocal space, and therefore opens up a gap in every single point in reciprocal space. And then here on the right, you have the example of a chiral p-wave order. So this is a superconducting order that has a strong dependence in momentum space. In particular, it has a winding number in reciprocal space. But then when you project it on the Fermi surface, it is capable of gapping the Fermi surface at every single point. Spectrally, these two superconducting gaps look the same. They are indistinguishable. But if you look at their topological properties, if you look at the Chern number associated with these superconducting states, then you see that they are completely different. The S-wave superconducting state has Chern number 0, whereas the chiral p-wave state has Chern number -2 or +2, depending on the chirality. And of course, this has a massive consequence when you think about a finite system. So in the case of a S-wave superconducting order, you effectively have a gap everywhere, both in the bulk and at the edge of the system. Whereas if you look at the spectra of a chiral topological p-wave superconductor, you see that you have a gap in the bulk, but then you have gapless edge states at the edges, ones that propagate in one direction and the other that propagate in the other direction. These edge states will become propagating Majorana modes. These modes are fractions of an electron, and this is what we are going to address later on. So now let us understand the emergence of these topological excitations. And for this, we are going to effectively look at the emergence of a new type of fractional excitation in an electronic system. This is what is called a Majorana bound state, sometimes as a Majorana fermion, and it's a direct consequence of Boglio of the Jens Hamiltonian. And let me emphasize how interesting this is, that you have an effectively single particle formulation that where you, of course, have to consider both electrons and holes, and yet, even though your formulation is single particle, you are capable of capturing an exotic state that arises due to fractionalization of an electron. So you can think that a Majorana bound state is 1/2 of an electron, and we are going to look at this in detail now. So the idea is that we start with our Hamiltonian for a superconducting state. We have our kinetic energy over here, and then we have our superconducting term on the right. Now, this Hamiltonian could be solved with our Nambu spinor, and our Nambu spinor had this electron part and this whole part, and we had to write down a Hamiltonian that was effectively a 4x4 matrix with the single particle eigen energies in the diagonals and with the superconducting order in the off diagonal. The important deal is that when you take that Hamiltonian and you compute the eigenstates of that Hamiltonian, you obtain that the eigenstates are usually a combination of electrons and holes. So they have a certain part on the electron component, another part of the hole component, and this is automatically a consequence of having a finite pairing term in the Hamiltonian. Now, a Majorana fermion is by definition a particle that it's its own antiparticle, meaning that you have some field operator for this quasi-particle, and effectively psi dagger is equal to psi, meaning that creating and destroying the quasi-particle is the same, which it is massively counterintuitive, but this is the mathematical definition that we have for a Majorana bond state. In plain words, this means that the particle is its own antiparticle, meaning that creating a particle is the same as creating an antiparticle. And so if you now think about the description of superconductors, then you see that in superconductor we have a combination of electron and hole. So one could argue that perhaps a superconductor is a good place to look for the emergence of these excitations. If you think about conventional materials in general, of course, it may be very hard to have Majorana fermions in a conventional material such as semiconductor, because of course, then in semiconductors, we only have electrons. We never have a quasi-particle that it's its own, let's say, antiparticle. However, one can think in a relatively simple way. So at least from a mathematical point of view, you can actually write down every single electron just as a combination of two Majorana quasi-particles. This is just an algebraic trick. This is something that works mathematically and that allows you to map every single fermion, every single electron to just two Majoranas. So you can think that destroying an electron is creating two Majoranas in this way, so with psi alpha and I psi beta, and creating the electron is just with the opposite sign. And if you enforce these algebraic relations, you will see that what you fulfill the fermionic statistics. So the idea of superconductivity is that you can actually sort of isolate one of these single field operators. You can isolate one Majorana state from the other Majorana state. So you can think that every single electron in nature, at least mathematically, can be expressed as two Majorana fermions. The only problem is that these two Majorana fermions, they are always together. They are always coupled. So you can never see one individually. But in a superconductor, thanks to the superconducting pairing, you may be able to just see one of them individually. You may be able to just get rid of one of these Majorana fermions. And the idea is what we mentioned before. So you can think that a Majorana fermion, in terms of conventional fermionic operators, is a combination of electron and hole, and automatically in a superconductor, we have this sort of combination. So if we take the right type of superconductor, we may get that the fundamental excitations are Majorana fermions. So now the important question is, what is this specific superconductor that allows us to create individual Majorana excitations? The answer to that is extremely simple, and it's effectively the simplest superconductor that you are capable of writing, which is a one-dimensional chain without a spin and with superconducting order. So here what we are taking is just our one-dimensional chain. So we have first neighbor hopping between site n and site n plus 1. And now we add superconductivity in the simplest way possible. So a term that is Cn is not allowed because of fermionic statistics, but there's a term that is Cn plus 1 that is allowed by fermionic statistics. And this term has, of course, two annihilation operators, and we have the complex conjugate over here, and this delta is our superconducting order. So now we can take this Hamiltonian real space, do a Fourier transform of our operators, and end up with our Hamiltonian in reciprocal space. And when you look at this in reciprocal space, what you actually see is that you have the dispersion of your linear chain, which is again 2 times cosine k. And then you have this anomalous term that has two creation operators and two annihilation operators, and that most importantly has a k dependence that it's odd in momentum space. So you have sign of k, which means that your superconducting order changes sign if you change the sign of k. So this is a spin triplet superconductor. And now, the really interesting point is that that very same Hamiltonian in real space can be automatically mapped to our dimerized model, and it can be mapped to the dimerized model in a very specific limit. If you take that the superconducting order is exactly the same as the hopping, you can actually take your Hamiltonian for the superconducting state and make the replacement in terms of Majorana operators. So now you say that every single site in your chain is represented by two Majorana operators, in particular Majorana operator 2n-1 and 2n. You plug this algebraic relation back into your Hamiltonian and you end up with this Hamiltonian over here. And the most important point of this Hamiltonian is that the first Majorana operator and the last do not appear in the Hamiltonian. So you can think that they have an eigenenergy that is zero. All the other terms, all the other Majorana operators, they remain in the Hamiltonian and they are coupled between neighboring sites, but the first and the last Majorana, they are uncoupled. And so if you now take this Hamiltonian and do some, let's say, brute force diagonalization, first in a periodic system, what you observe is that, of course, this delta opens up a gap in reciprocal space, and this gap is the superconducting order. So in a periodic system, you have a band structure that shows a gap, and this band structure actually has a finite topological invariant. It has a finite subphase. The most interesting thing is if you look at this very same Hamiltonian, not in a periodic system, but in a system with open boundary conditions. So on a chain that has 100 sites, for example, and that the first site is not connected to the last. If you do the calculation of the electronic spectra, in this case, what you actually observe is that you have a gap for most of the states, but there are some states that are exactly pinned at zero energy. And if you look at the location of these states, you see that they are located on the edge. These modes are the topological modes of the superconductor. These modes are the Majorana states that did not appear in the Hamiltonian when we did the change of variables from fermionic operators to Majorana operators, and these are the topological modes associated to the topological invariant that you observe with periodic boundary conditions. And so the idea that those topological zero modes, they are actually extremely robust. So now you can start thinking about not taking delta as the same as the hopping, but to have a finite delta and to even have a finite chemical potential. And if you do that, you will see that those zero modes, they remain there, at least if the chemical potential is not too large. And the reason for that is because those zero modes are topological modes, and they are the topological modes associated to a p-wave superconducting state that, due to its non-trivial topological invariant, has associated Majorana modes. And so in practice, in the case where you have fine tuning, so delta is equal to t, there's no chemical potential, you can actually show that the Hamiltonian can be mapped in the Majorana representation to the dimerized model that we saw in our recording for topological physics. And in particular, the two uncoupled Majorana modes correspond to this mode at the beginning and this mode at the end. So you can think that in the Majorana representation, this one-dimensional topological superconducting model effectively maps to our dimerized model where we had strong coupling between two sites and no coupling whatsoever between the other two sites. And then, of course, the model also has a trivial phase, which appears when your chemical potential is much, much bigger than any other energy scale. And in this trivial case, essentially each Majorana mode is coupled within each site. So you can think that this is the limit where your Majorana modes are confined and they form a single electron. And this is the limit where one of the Majoranas is deconfined, in particular for the site at the beginning and the site at the end. And of course, in this topological case, we get an H mode that is a topological state that is our Majorana zero mode. Of course, one of the important questions is, well, how can we create a topological superconductor? As we mentioned before, P-wave superconductors are very rare in nature, so very often we need to create them artificially. So there are, of course, many different ways, but let me mention just one of them in connection with one of our previous recordings, that it's based on just using another topological state, that it's the quantum spin Hall state. So if you have a quantum spin Hall insulator, like for example, tungsten ditelluride, you can think that in one of the edges, you have helical mode. So up electrons move in one direction and down electrons move in the opposite direction. Now what you can do is you can put magnets on the sides so that this region over here remains insulating because you destroy locally the helical states because you break transversal symmetry. In this region over here, you also destroy your topological states just because you break transversal symmetry. So you effectively end up with a helical gas only on this edge that is disconnected from the other edge. Now, a helical gas, in a way, is like up electrons moving one direction and down electrons moving in the opposite direction. What this actually means is that when you add a superconducting state, you are effectively emulating a spinless system with superconductivity. And it's spinless because you have up electrons moving to the right, but you don't have down electrons moving to the right. So if you think in terms of how many electrons move in one direction and how many electrons move in the opposite direction, then you have effectively a spinless system. So there's no spin degeneracy. And when you introduce superconductivity in a system that has no spin degeneracy, you effectively map to our one-dimensional model for P-wave superconductivity. So this is one of the ways to get Majorana bound states. So you take a quantum spin Hall insulator and you put a superconductor. Now, let me briefly tell you about one of the biggest consequences of Majorana bound states, which is their potential use for topological quantum computing. The fundamental idea is that Majorana states, they are not exactly fermions in a sense that they don't pick exactly a minus sign when you move one around the other. And this is something that one can automatically get from the value of the Jens Hamiltonian if you consider that you have several Majoranas. So the idea is that Majoranas pick non-trivial phases, and the fact that you have quasi-particles that pick non-trivial phases when you break one around the other essentially allows you to do computations by changing them. You can actually do a topological quantum computation just by moving Majoranas around. One of the most interesting points about Majorana states is that, of course, they are topological excitations, so they are very robust to things that, like, let's say, decoherence, and one can even argue disorder if it is weak enough. So computations using Majorana excitations could actually be one of the ways to go towards a quantum computing algorithm that actually does not suffer from decoherence. And let me briefly tell you what is the idea behind this. So let's imagine that you have a system that has 4 Majorana states. This actually means that this system encodes 2 electrons because, of course, each electron is formed by 2 Majoranas. And you can think that you have some operational basis that corresponds to the different fillings that you have of your electronic system. So you have the empty state, you can have the state where you fill one of the electrons, you can have the state where you fill the other electron, or you can have the state where you fill both of them. And the idea is that Majorana excitations essentially give rise to a degeneracy in this manifold. So all these states are degenerate, and this is an automatic consequence of having 0 modes associated to your Majorana excitations. So since they are degenerate, one could actually think about using that as a computational basis for a quantum computation. And the basic idea is that if you think about taking just 2 Majoranas and winding 2 of them, you can actually show relatively easily that the ground state actually picks a phase when you break those 2 Majoranas. And that phase that you pick is essentially the exponential of pi over 4, the product of the 2 Majoranas. Now, the important point is that you can play this game with any pair of Majorana. So you can take the pair 1, 2, you can take the pair 3, 4, you can take the pair 1, 4th, and so forth. And braiding one with respect to the other is not commutative, meaning that the order in which you do things actually matters, which in algebraic terms, it means that you have a non-abelian algebra. Braiding 1 and 2 and 3 and 4 is different than braiding 3 and 4 and then 1 and 2. And this non-abelian algebra essentially means that you can do non-trivial operations with the Majoranas just by braiding them one around the other. So Majorana excitations are one of the ways of going for topological quantum computing. And it is one of the strategies that, if it works, it would allow to create qubits that do not suffer from decoherence, thanks to the topological protection that Majoranas have. And so to finish the session, and if I can ask you to remember something, please remember that superconductivity arises from attractive interactions, that our different superconducting states can be captured at the mean field level just by adding a superconducting mean field order with the right symmetry. And that, of course, this symmetry of the superconducting order allows us to classify different types of superconductors, and that there's a very specific type of superconductor that are called topological superconductors that show Majorana excitations that may provide one way for topological quantum computing. Thank you so much for your attention.